Hi, welcome back to Engineering Mechanics series. This is Moses, and in this lesson I want to talk about the resultant force on a point. You would remember in the previous lesson we talked about the net forces upon a body, and we said that if the net forces upon the body are equal to zero, then the body either continues to be in the state of rest or of uniform motion according to Newton's first law. But if there is a net force, then the body will accelerate in the direction of the net force and proportional to the force. Right, so let's now focus on how do we really calculate this resultant force or the net force. If there are multiple forces being applied on a body like this, here you have a bracket where there are three different forces on that point. 80 newtons, 120 newtons, 150 newtons, etc. So how are you going to determine the equivalent of the net force upon a point? We're only talking about a point. We will come to a body later on. If they are applied on a body at different points, then the analysis will be slightly different. But at the moment, we'll look at forces upon a point. Now, let's consider this point. You have this x and y axis and this point A. Let's say this is a force applied on point A, which is 50 newtons and at an angle of 15 degrees. And there's another force applied of 30 newtons at an angle of 60 degrees. So the terminology that we use is magnitude and direction. So magnitude is 50 newtons and 30 newtons. That's the size of the arrow. And direction is the 15 degrees and 60 degrees. So when you have a magnitude and direction, it is known as a vector. A vector has a magnitude and a direction. Okay, so these forces are really vectors. So we will deal with this subject using these concepts of vectors. So how do I calculate or how do I determine the equivalent or the net force on point A from these two different forces? So the best method to do graphically, let's start graphically first. That is, we're not going to calculate, but we will graphically determine the magnitude and the direction of the net force. So what we need to do is we just need to draw parallel lines like this. Draw a parallel line on the top of the second force parallel to the first force, and draw a parallel line at the top of the first force parallel to the second force. Is basically create a parallelogram as I have shown here in this figure. And all you need to do then is to join the diagonal points and you get a resultant force. So this is the resultant force of 74.3 newtons approximately and 31.6 degrees of angle from the x-axis. And this is the resultant. So you can actually determine this graphically by constructing that graphically and measuring it, both the angle. You can measure the angle, measure the distance, and you can find out the resultant force. You could do it in a slightly different way known as a triangular method. And how do you do this? Let's take these two forces that we've already looked at. Okay, you just need to move the second force on the top or the tip of the first force. So move the second force without changing the direction. Just move it and place the starting point of this second force onto the ending point of the first force. Right, so that's how you need to do it, because at the tip of the arrow is where you need to place the bottom of the second force. Okay, once you do that, you join the point A to the top tip of the second force and you get the resultant force, which is the same as what we have determined previously, 74.3 newtons and 31.6 in angle. There is another method. What if there are more number of forces? Let's say, we call Polygon method, but I'll explain. Let's say there is a force V1 in this direction. The angle and the and the magnitude are apparent. You can see the size of the arrow and the angle at which it is plotted. I don't want to give the exact angles here, but let's take this example. This is V1 and this is V2, V3, V4. So you got these forces in all directions with all different magnitudes. How are we going to determine the equivalent force on the point A, which is the center, which is at the center? Right, so what we do then really is to move like this. So move the V2 on the tip of V1 and move V3 on the tip of V2, move V4 on the tip of V3. If you got more forces, move them all. If they crisscross, that's fine. Okay, just follow this method. Once you do that, then join the starting point, the central point, to the tip of the last vector like this, and that is your resultant force. So the resultant force of all these four forces is essentially that red line. Okay, so you get the magnitude and you also get the direction of this, and you can do this graphically. You can measure the length of that red line. You can also measure the angle of that red line with respect to the positive x-axis. Okay, right, let's come back to the same example. I want to mention the concept of coplanar forces or coplanar forces. What does coplanar forces mean? This is a term used many times in engineering mechanics. It means that all these forces are in a plane, So here the plane is XY plane. For example, there are systems in 3D. Sometimes the forces are not all in a single plane, so that they are not coplanar. And here in this case, they are all flat in a single plane XY. Therefore, they are coplanar. There is also another term, concurrent forces. Concurrent means all these forces are applied on a single point. Concurrent. They all intersect at a single point. That's the word for concurrent. There is another word for collinear. I will talk about that later on. So these two things you must remember: coplanar forces and concurrent forces. Now let's draw the lines on each of these forces. So these are known as lines of actions. And it is possible you can move these forces along the lines of actions without affecting the net effect. There is no change in net effect. You can move the forces. Imagine the force acts, it acts like a pushing force rather than the pulling force from the other side. It doesn't matter. As long as the force is on the same line of action, then there is no change in effect as far as the net force is concerned. Okay, but the net force always is to be acted upon at the on a line of action passing through the point at which we were considering, the center point. Okay, but these are the lines of action. So if you take a force on a line of action and put another force on the same line of action, they are called collinear forces. Okay, collinear forces. You got coplanar forces, concurrent forces, and collinear forces. Here in this case, all these forces are not collinear, as they have different lines of action. So the lines of actions are the lines that I have drawn here. Now let's follow the polygon rule, and let's say we would determine the equivalent force. Now this magenta colored force, the effective resultant force, is the resultant force but notice it is not at the center. The actual thing should have been here, the red one. And so by moving, if you try to determine geometrically and end up with a magenta one, and if you think that the line of action has shifted from the center, now that is wrong. This polygon method will give you the magnitude and the direction of these the resultant force, but you need to apply that resultant force on that point that we are considering in our calculations, okay? And the line of action has to intersect that point. Otherwise, there will be a moment created. Just you need to observe that. Right, let's come back to the original problem. Let's talk about resolving the forces. Resolving. What does resolving mean? It means that we take the components of this force on the y-axis and x-axis and the y-axis. So let's take V1, the force V1. Well, before that, so why do we take the resolving? To calculate it numerically. So far, we've looked at determining the resultant force using geometric method, right? Where we have to measure the magnitude and measure the angle. Whereas in this case, we want to actually calculate the value. So how can we calculate? And for that, you need to resolve the vectors. Take the resolution of the vector on the x-axis and on the y-axis. How do you do that? Let's take V1 is a vector. This is the green arrow that you see here is the x component of the vector V1. And this magenta one here is the y component of the vector V1. All that you need to do is draw a parallel line to x and to y at the tip of the arrow, and then you can draw from the origin the x component and the y components. Very simple. This is the x component for V2, and that is the y component for V2. And I have here the x component for V4 and y component for V4. So you can resolve any force in the x direction and in the y direction. And why do we do that? In order to get the effective force. So how do we get the effective force? Calculate all the x components. How do I calculate the x components? If you want to do graphically, you could just measure the length of that arrow that I showed you earlier, the green arrow and the magenta arrow. But in this case, we are interested in determining the resultant force numerically using calculation. So how do you do that? You take the vector, the magnitude of the vector V1, and multiply it with the cos of the theta, the angle that it is making. So V1 cos theta 1 is the x component. So take the cosine of the theta that the vector V1 makes with the x-axis, okay? And similarly, if you want to get the y component, you need to multiply the magnitude of the vector with the sine of the theta. So V1 sine theta 1 is the y component, and calculate all the x components, calculate all the y components. But you just need to remember that the theta that you use, the angle, must be from the positive side of the x-axis in anti-clockwise direction. Always this is the case. Otherwise, you will end up taking a wrong angle, and your results of sine and cos will be wrong, and you get wrong results. Take the angle that I have shown you. Now for V4, you need to go all the way from the positive x-axis round back to the place where the vector V4 is, and so that will be more than 180. It is less than 270, somewhere in the middle, and that's the angle. So that's the sort of angles that you need to first take and calculate the x components, calculate the y components. When you sum up all the x components, straightforward sum. If some of them are negative, obviously when you sum it, those will be negated. Take the sum, you get Vx. Take the sum of the y components, you get Vy. And from this to these two values, Vx and Vy, you can get the net force. And how do you get it? So this is the net force, the red one. So the magnitude of the force is calculated by squaring Vx and Vy, adding them and taking a square root. Square root of Vx square plus Vy square. And if you want to calculate the theta, the angle that is subtended by the red line with respect to the x-axis, positive x-axis, the theta is essentially the tan inverse, arctan of Vy over Vx. So use this formula, you can calculate the magnitude and you can calculate the angle of the resultant vector. So this is how to determine the equivalent or the net force or net effect of all the forces that are acting upon a body. And if this net effect, if Vx equal to 0, if Vy equal to 0, then the whole system is in equilibrium. That is not going to move. And that is what we have considered in some of the examples that we have seen earlier in the previous lesson. I hope this is useful for you. I will see you in the next lesson. Thank you very much.